Hello everyone. In lecture number 21 we have discussed the Carnot cycle, and at the end of discussion on Carnot cycle we cited two Carnot theorems. Here in this lecture number 30, we are going to prove these Carnot theorems. The first Carnot theorem was a reversible engine is more efficient than an irreversible engine. So in this regard we have to start by connecting a source with a sink so that the source temperature of the source T1 is greater than that of the sink T2. Okay. These two, when connected with an irreversible engine I, then this one withdraws Q amount of heat and performs W1 amount of work, and Q minus W1 amount of heat is deposited to the sink. And when the source is connected with a reversible engine R, then it withdraws the same amount of heat Q, but it performs some other amount of work W2, and it rejects, after having performed W2 amount of work, it rejects Q minus W2 amount of heat to the sink. So we have an irreversible engine I and a reversible engine R. The corresponding efficiencies have been assumed to be eta 1 and eta r respectively. Okay, and let us assume that this is not eta 1, I'm sorry, this is eta I, that means efficiency of the irreversible engine, and this is efficiency of the reversible engine. Let us assume this arbitrarily, that efficiency of the irreversible engine is greater than that of the reversible engine. That means we are contradicting the first Carnot theorem. Okay, let us see whether the opposite statement is correct or not. Okay, so we are assuming that efficiency of the irreversible engine is greater than that of the reversible engine. So it is possible only when the work performed by the irreversible engine W1 is greater than the work performed by the reversible engine W2. So if it is assumed that eta I is greater than eta r, then it is also assumed that W1 is greater than W2. Okay. Now suppose the engines are operating between the source at temperature T1 and the sink at temperature T2, so that T1 greater than T2. This is said already. And for engine I, heat supplied by the source is Q. Okay. Work obtained is W1, and heat rejected to the sink is Q minus W1. Let's redraw this picture here again. When you are taking the note, you need not draw this again, because for my convenience I am just bringing this picture diagram here. Okay. So let's see. Q amount of heat withdrawn, W1 amount of work done, and W minus Q1 amount of heat deposited to the sink. Conversely, for the reversible engine, heat supplied to from the source or by the source is Q. Okay. Work performed or work obtained is W2. Okay. Look at the direction of the arrow. That means arrow is outward direction, means work is done by the engine. And here Q minus W2 amount of heat is rejected to the sink. So we have already assumed that W1 is greater than W2. Then what about Q minus W1 and Q minus W2? Definitely, if W1 has greater value, then Q minus W1 should have lesser value. So Q minus W1 is less than Q minus W2. Up to this it's okay, no problem. Now let us carry out a cyclic process in which engine I is performing the forward process while engine R is performing the backward process, like this diagram. Here look at the direction of the arrow. This is as usual like the previous diagram, but this one has reversed its direction. Okay, it was in the previous diagram going from left to right, but right now it is withdrawing heat from the sink and depositing heat to the source. And here look at the direction of the arrow of the engine. Here the arrow is towards the inward direction. That means work is done on the system. Okay, here work is not obtained. You have to provide some work to the system. That means you have to provide some energy. It may be electrical energy or something else. Okay, that is why it is red colored, and it is the direction of arrow. Instead of outward direction, it is inside the into the inward direction. Okay, so this way we have completed a cycle here. Okay, so what about the description of this cycle? Q amount of heat is withdrawn, W1 amount of work is performed by the irreversible engine, then Q minus W1 amount of heat is deposited to the sink. Now from the sink, Q minus W2 amount of heat is withdrawn. Then W2 amount of work is provided from outside. So this work is combined with this one. So Q minus W2 plus W2 becomes Q. So the Q amount of heat is deposited or rejected to the source. This way the cycle is completed. Let's see the description. The amount of heat supplied by the source is Q to yield W1 amount of work, and Q minus W1 amount of heat is rejected to the sink. Whereas Q minus W2 amount of heat is taken up from the sink by performing W2 amount of work to return the same Q amount of the heat to the source. Okay. So in this complete cyclic process, the source has not ultimately lost any heat. Why it should lose any heat? Because the source is, here look at the picture here again, it is releasing Q amount of heat and receiving Q amount of heat. So is it losing anything? No, it is not losing any heat. Okay, so this is described here. In this complete cyclic process, the source has not ultimately lost any heat. But what about the sink? It has a different experience. It is absorbing Q minus W1 amount of heat but losing Q minus W2 amount of heat. So there should be some difference. So the coupled engine had yielded, due to that difference, W1 minus W2 amount of work, because W1 is greater than W2. So this amount of work has been yielded. Okay, so since this amount of work is yielded, this is done in lieu of the heat lost by the sink. What about the amount of heat lost by the sink? Now it is Q minus W2, absorbed heat minus lost heat. Okay, so minus Q minus W2 minus Q minus W1. Sorry, this is not lost heat minus absorbed heat. Okay, Q minus W2 is the lost heat and Q minus W1 is the absorbed heat. So this is equivalent to the work obtained, because the result is what? Q minus W2 minus Q minus W1 is nothing but W1 minus W2. This is nothing but W1 minus W2. Okay, so this is equivalent to the work obtained. That means what? That means heat is extracted from a lower temperature body to produce work. Is it supporting the second law, or is it actually following the second law? The answer is no, it is not at all following the second law. It is contradicting the second law. So this is in contrary to the second law of thermodynamics, and hence it is not possible, because otherwise it would have become the perpetual motion of second kind, and in reality this is not possible. So the opposite statement of the Carnot Theorem 1 is wrong. Okay, that means efficiency of the reversible engine is not greater than reversible engine. So it's opposite direction. That means the statement which is given in the Carnot Theorem 1 is correct. That means the efficiency of the reversible engine is always greater than that of the irreversible engine. Therefore, a Carnot engine which is reversible is more efficient than other engines which are irreversible. Hence, it has been established that this is the Carnot's first theorem. What is the theorem? A reversible engine is more efficient than an irreversible engine. Now, let's move on to the second Carnot theorem. What is the second Carnot theorem? Now, all reversible engines are equally efficient working between the same temperature limits. So in this regard, we have to take the same temperature limit T1 and T2, so that T1 is greater than T2. Now here R1 is one reversible engine which is connected from the source to the sink. It is withdrawing Q amount of heat from the source and performing W1 amount of work and rejecting Q minus W1 amount of heat to the sink. On the other hand, if another reversible engine R2 is connected from the source to the sink, then it is also taking up the same Q amount of heat from the source by performing W2 amount of work and then rejects Q minus W2 amount of heat to the sink. So let's describe. Let's take two reversible engines R1 and R2 working between the source at temperature T1 and sink at temperature T2, so that T1 greater than T2. R1 can perform W1 amount of work, whereas R2 can perform W2 amount of work, both by taking up Q amount of heat from the source and rejecting Q minus W1 amount of heat to the sink and Q minus W2 amount of heat to the sink respectively. Now, if it is assumed that a cyclic process is carried out so that R1 is performing in the forward direction and R2 is performing in the backward direction. Here, look at the previous picture. Here, R1 to R2 has one direction from the source to sink, while here also, I'm sorry, this is not R1 to R2, this is source to sink. Source to sink has the direction for R1 from left to right, while the same direction is followed by the reversible engine R2, which is also performing from left to right, but the heat flow is taking place from left to right. This is the direction. But look at this picture right now. Here, this direction has been changed. Okay, it is now heat flow is taking place in the reversed direction. Instead of source to sink, heat is now going from sink to source. Okay, source is giving away Q amount of heat and taking up Q amount of heat. Okay, but the sink has a different story. It is actually absorbing Q minus W1 amount of heat while it is releasing Q minus W2 amount of heat. Okay, so let's describe this. R1 takes up Q amount of heat from the source, produces W1 amount of work and rejects Q minus W1 amount of heat to the sink, while R2, this engine is taking up Q minus W2 amount of heat from the sink, and from outside W2 amount of work is being provided. Okay, and this W2 is combined with this heat, so Q minus W2 plus W2 equals to Q. So Q amount of heat, this is Q minus W2 plus W2. Okay, so Q amount of heat is deposited to the source. So thus the cycle is completed. Now let us assume that any one of the reversible engine is more efficient than the other reversible engine. Okay, that means we are trying to contradict the second Carnot theorem here. So if it is assumed, then this is also automatically assumed that the work W1 is greater than the work W2. Okay, the work performed by the first engine should be greater than that of the second engine. Okay, let me recall the diagram here. You need not draw this while taking the note. Just for my convenience, I am redrawing here. Okay, so the heat absorbed from the sink, okay, the temperature of the sink is colder. Okay, it is colder than the source, than that of the source, minus that of the heat which is rejected to the source, which is the hotter body. Okay, so Q minus W1 amount of heat is absorbed, Q minus W1 amount. Okay, this is subtracted from the amount which is taken up from the sink. The amount of heat which is taken up from the sink is what? Now Q minus W2. So Q minus W2, that is the heat absorbed minus the heat rejected. That is heat absorbed from the colder body and heat rejected to the hotter body. And this way W1 minus W2 amount of work either is produced or is provided. Let's see what is the value, whether it is positive or negative. This is definitely a positive value because W1 has been assumed to be greater than W2. This is what is positive. That means work is being produced here, not you have to provide from outside. So can you think that you are taking up heat from the colder body and rejecting heat to the hotter body, and in this regard you are performing some work, that you are performing some amount of heat into work, and that amount of work is W1 minus W2. Is it possible? Look, heat supplied by the lower temperature body is completely converted into work, which is actually contradicting the second law of thermodynamics. So this is in contrary to the second law of thermodynamics. Okay, that means both the engines are equally efficient. None of them are more efficient than each other. Okay, thus it has been established the second Carnot theorem. What is the second Carnot theorem? Now it is all reversible engines are equally efficient working between the same temperature limits. Okay, So that's all for today. Thank you. Have a nice day.